In this episode, we are going to understand the fundamental principles of highway design. We will see how lane requirements are determined, why medians are important, the role of service roads, the importance of T-junctions, the role of roundabouts, the importance of interchanges and grade separation driver psychology in highway engineering, and how proper highway planning improves safety and traffic flow. And remember, advanced topics such as circular curve design, transition curve design, super elevation, stopping sight distance, and vertical curve design are already discussed in detail in separate videos in this channel. And also, the road construction procedures in extreme climatic zones are discussed in detail in separate videos in this channel. So please watch this episode carefully till the end. Do you want to learn the real secrets of civil engineering, the kind of knowledge most experienced engineers never share? Welcome to Civil Guru Solutions. This channel is dedicated to revealing the hidden side of civil engineering and explaining it in a simple, practical, and easy-to-understand way for everyone. To make learning accessible worldwide, our videos are available in multiple languages. You can choose your preferred audio language from the YouTube settings at the bottom of the screen. If you find our content helpful, please like, comment, share, and subscribe. Chapter 1. Principles of Highway Design. The first principle of highway design is safety. A highway must be designed to forgive human mistakes. Drivers may become tired, distracted, or overconfident. Therefore, roads are engineered to reduce the possibility of accidents and minimize damage if accidents occur. This is why highways use proper lane width, safe curves, shoulders, medians, barriers, road markings, drainage systems, and sufficient visibility distance. But safety alone is not enough. A modern highway must also provide smooth traffic flow, driving comfort, fuel efficiency, economical construction, low maintenance, and long service life. This balance between safety, economy, and efficiency is the true philosophy of highway engineering. Chapter 2. How the number of lanes are calculated. Now let us understand one of the most important questions in highway engineering. How do engineers decide whether a road should have 2 lanes highways, 4 lanes highways, 6 lanes expressways, or even 8 lanes expressways? The answer depends mainly on traffic volume, traffic composition, vehicle speed, terrain condition, future traffic growth, and desired level of service. The first step is traffic survey. Engineers conduct classified traffic counts, turning movement surveys, origin-destination studies, and peak hour analysis. The traffic is then converted into PCU, passenger car units, because a truck, a bus, a motorcycle, and a car do not occupy the same road space or move at the same speed. For example, one heavy truck may equal multiple passenger cars, while motorcycles occupy less roadway space. Therefore, traffic is standardized into PCU values. This concept is used widely in IRC, AASHTO, and highway capacity analysis. Next, engineers calculate AADT, which means annual average daily traffic, and also design hourly volume, because highways are not designed based only on average traffic. They are designed for future peak traffic conditions. Generally, the peak hour traffic may be around 8 to 12% of total daily traffic. Now comes the important engineering concept, design service volume. The design service volume represents the maximum traffic that can pass safely and efficiently through a highway section while maintaining acceptable driving conditions. According to IRC recommendations, a standard lane under ideal conditions may carry approximately 2,000 passenger car units per hour for a single lane under ideal conditions under uninterrupted traffic conditions. However, in real-world highways, capacity reduces due to heavy vehicles, side friction, intersections, terrain, pedestrian movement, roadside activities, and access points. Therefore, actual lane requirements must be adjusted carefully. For example, If projected peak hour traffic is around 4,000 passenger car units per hour, then a two-lane highway may become insufficient. In such situations, engineers may recommend four-laning to maintain safe traffic flow and acceptable level of service. Similarly, when traffic continues increasing, the highway may later expand into 6 lanes or that is 8 lanes. This is why many modern expressways reserve additional land for future widening. Now, another important concept is level of service, commonly called LOS. LOS describes the quality of traffic flow experienced by drivers. It ranges from level of service categories, from Category A, which represents free flow traffic, to Category F, which represents severe congestion. Modern highway design tries to maintain traffic operation within acceptable LOS conditions for future traffic demand. This is why highway planning is not only about present traffic, it is actually about predicting how millions of future vehicles will move safely for the next 20 to 30 years. Chapter 3. Central Medians. As highways become wider, traffic moving in opposite directions must be safely separated. This is the purpose of the central median. The median acts as a protective buffer zone between opposing traffic streams. It significantly reduces head-on collisions, glare from headlights, and uncontrolled vehicle crossing. Median widths vary greatly depending on available land and highway category. Some medians may be as narrow as 1.2 meters, while expressways may use very wide landscape medians. Where the median width is small, raised concrete curbs or crash barriers are introduced in narrow medians. In wider rural medians, standard raised median curbs are generally around 150 mm to 300 mm. Sometimes the open separation itself is sufficient. At U-turn locations, adequate storage space must be provided for waiting vehicles. Otherwise, traffic may spill into moving lanes and create dangerous conditions. Openings in medians should never be introduced randomly. Particularly, openings in medians should not be introduced at the point of small link roads. Improper median openings are one of the major causes of highway accidents. Chapter 4. Service roads. Now let us understand the role of service roads. Service roads, also called frontage roads, run parallel to the main highway. Their purpose is to separate local traffic from high-speed highway traffic. This becomes extremely important near residential areas, commercial developments, fuel stations, industries, and urban corridors. Without service roads, local vehicles may directly enter the highway, creating dangerous conflict points. Service roads help reduce accidents, improve pedestrian safety, support local business access, reduce traffic interruptions, and improve highway efficiency. They also provide safer zones for loading and unloading commercial vehicles. However, service roads require additional land, proper drainage, and careful visibility planning. Poorly designed service roads can create confusion and unsafe merging conditions. Chapter 5. Highway Geometric Design. One of the most important parts of highway engineering is geometric design. Geometric design controls alignment, curves, gradients, visibility, and vehicle movement behavior. If a curve is too sharp, vehicles may lose stability. If visibility is poor, drivers may not react in time. If gradients are excessive, heavy vehicles may slow down and create congestion. To solve these problems, engineers carefully design horizontal curves, transition curves, super elevation, sight distance, and vertical curves. These topics are extremely important in highway engineering. Therefore, we already discussed them separately in detailed videos available in this channel. Please refer to those episodes for complete engineering explanations and calculations. Chapter 6. T-junctions and link roads. Now let us move to intersections. Intersections are among the highest accident-prone areas on highways. At locations where village roads, minor roads, or local roads connect with highways, proper junction planning becomes essential. A poorly designed junction can create sudden braking, blind spots, side impact crashes, and traffic congestion. At major highway intersections, engineers develop proper T-junctions using channelizing islands, lane separation, and controlled turning movements. These features help drivers slow down safely, identify priorities clearly, and enter highways smoothly. Simple village road connections, however, may only require basic link roads without large traffic islands. Good T-junction design provides better traffic control, reduced head-on collision risk, improved visibility, and safer turning operations. Chapter 7. Roundabouts. Now let us understand roundabouts. A roundabout is a circular intersection where vehicles move in a single direction around a central island. Vehicles entering the roundabout must give way to vehicles already circulating inside. Unlike signalized intersections, roundabouts naturally slow down vehicles. This reduction in speed greatly reduces accident severity. A properly designed roundabout improves traffic flow, reduces delay, lowers maintenance cost, and improves intersection safety. The central island and curved entry geometry force drivers to reduce speed before entering. This is an excellent example of highway engineering working with human psychology. However, roundabouts must be carefully designed for buses, trailers, emergency vehicles, cyclists, and pedestrians. Otherwise, large vehicles may struggle to maneuver safely. Chapter 8. Interchanges and grade separation. As traffic volume increases further, normal intersections and even roundabouts may become insufficient. At very high traffic corridors, vehicles crossing each other at the same level can create severe congestion, long delays, and high accident risk. To solve this problem, highway engineers introduce grade-separated interchanges. An interchange allows vehicles to move between highways without directly crossing traffic streams at the same road level. Instead of stopping traffic, vehicles move continuously through flyovers, underpasses, ramps, loops, and directional connectors. This concept is called grade separation. The primary objective of an interchange is to eliminate conflict points, because in normal intersections, vehicles may conflict through crossing movements, merging movements, diverging movements, and turning movements. Interchanges greatly reduce these crossing conflicts. As a result, traffic flow improves, vehicle speed increases, fuel consumption reduces, and accident probability decreases. Different types of interchanges are used depending on traffic volume, available land, design speed, and highway category. Some common interchange types are diamond interchange, cloverleaf interchange, trumpet interchange, directional interchange, stack interchange. Large urban expressways often use multi-level interchanges to handle extremely high traffic volumes. However, interchanges are among the most expensive highway structures because they require large land area, bridges, retaining walls, drainage systems, lighting, and complex traffic engineering. Therefore, they are introduced only where traffic demand justifies the cost. Modern expressways and access-controlled highways heavily depend on interchanges to maintain uninterrupted high-speed traffic flow. Chapter 9. Drainage and durability. Now comes one of the most critical topics in highway engineering: drainage. Water is the biggest enemy of roads. Even a perfectly constructed highway can fail rapidly if drainage is poor. Water infiltration can cause potholes, cracking, rutting, shoulder failure, and pavement collapse. Therefore, highways are designed to remove water quickly from both the surface and subsurface layers. This includes camber, cross-slope, side drains, culverts, filter layers, and stormwater systems. Good drainage design directly increases pavement life. Chapter 10. The human side of highway design. Modern highway engineering is not only about vehicles, it is also about human behavior. Drivers subconsciously expect roads to behave consistently. Sudden narrow lanes, unexpected curves, or confusing junctions can create panic and increase accident risk. Therefore, highway engineers try to maintain consistent geometry, predictable alignment, proper signs, smooth transitions, and clear visibility. This concept is called driver expectancy principle. Good highway design works with human psychology, not against it. Before ending this episode, let us quickly summarize what we learned today. A highway is not merely a paved road. It is a carefully engineered transportation system designed using principles of safety, efficiency, comfort, durability, drainage, visibility, and future traffic planning. We learned how lane widths are determined, why medians are important, the role of service roads, the importance of junction planning, and how roundabouts improve safety. We also understood that advanced geometric elements such as circular curves, transition curves, superelevation, stopping sight distance, and vertical curves play a major role in highway safety and are discussed separately in dedicated videos on this channel, because in highway engineering, even a small design decision can affect thousands of vehicles every single day, and that is why highways are often called the arteries of a nation. If you enjoyed this episode, please like, subscribe, and share this video with your friends. Thank you.